Hello, everybody. So this gets us started into module 6 now, I think. So moving along, there's 8 modules, but we're doing it in 16 weeks, so stretched out for quite a ways. But now that we're at number 6, it kind of seems like the end's in sight. A few things to go over this evening. First thing I want to do is what we ran out of time for the other day, and that's something I would like to try to cover somewhere with the exception handling, and that involves actually fixing a problem, because tutorials and textbooks by their very nature have to be concise and to the point, so they always just go with the standard example of print out a custom message, but printing out a message is what happens by default if there's an exception occurs. So that's not really fixing the problem. So I wanted to do an example, a small example of that. And then we'll get into some data structure stuff, which is another thing about textbooks that always need to be kind of concise and to the point. And especially with stacks. We saw that the other day when we were kind of quickly looking at recursion, which isn't used as much as it used to be. I think I forgot to explicitly state this point. Like, it's faster and everything, but it was much more useful before the days of parallel processing and multi-threading. Well, we saw it in the Zoom call the other day when there was a lot of stuff going on. The resource intensive, like hardware intensive usage from recursion tends to slow down. But back in the day when that was the only thing happening, or if you're on some sort of specialized machine where there's not going to be a lot of other stuff going on, then recursion can be a lot faster. Okay. It's natural to the machine. Some of our languages don't have loops. Python does. So that's a nice loop, so we don't have to worry about that. So recursion can be faster, but we saw when I quickly drew a diagram that it naturally creates a stack. So a stack sort of data structure, which I'm pretty sure everybody's heard that term before because I use it quite often. We're going to look at that more formally this evening. That's what's natural to the machine, and we kind of have that in Python already. So to talk about it seems redundant, right? But and the textbook does a basic, a very stripped down version of making their own custom stack. To the point I was actually laughing when I was getting this lecture ready originally, because I noticed that when they wrote their pop method, all they did was call the pop method on the list. It's like, yeah, that makes it seem extra redundant. But I'm also going to take that a step further and actually show why we study the custom ones, because that stack that's built into the language is generalized. Right? Yeah, it needs to be an all-purpose one. But when we're making a particular piece of software, let her in real quick. Okay, yeah, so the thing is, the reason we look at them is when that stack that's built into the language, that's generalized, it has to handle any situation a programmer might need. But when we're making a specific piece of software, we know what our needs are. So we don't need the generalized version. So we can cut out some of the overhead that comes with that generalized version by making a custom one. And a few other features that aren't quite built in there, because again, it's a generalized thing. So gonna go through those, and then we'll take it a step further than the super basic examples like the textbook just went through the most basic thing, and it's kind of hard to see why we study these structures. It's like, aren't these at least something similar built into the language already? And in most modern languages, yes, but those are generalized. And when we're making a piece of software, we know exactly what our needs are. So sometimes, especially when we're doing big things, huge, massive pieces of software, or software that's intended to work with massive data sets. I mean, I think I've used the example before when I was taking a class on R, one that's usually used in statistical analysis situations. The data set we used for our class examples was all of the cholesterol data in America, since doctors have started keeping records. So we had like date of birth, date of death where applicable, enough cells to calculate people's BMI, and then their HDL and LDL. But all of it for every living American and some no longer living Americans. That was a huge data set. So when we're working with things like that, we want to try to specify a little, take out some of the overhead and cut out some of those extra costs. So we're going to look at those this evening, and also just sort of, while getting into data structures, we're not going to look at all of them tonight. We're going to start looking at them and talk about them tonight, because another part of it is they're built into our language, but it's a core part of what programmers work with, one of our core tools. So we want to make sure we understand what they're doing, and that we're using the right one for the right situation. But first off, that thing that we ran out of time for the other day. I'll go ahead and pull up my, go ahead and share my screen and just do this for an example. The standard for introducing exception handling in tutorials and textbooks, which by their very nature must be concise, is they just spit out a message. So let's say we have a file that depends on some other stuff, which one of the things we're going to do very, very soon, when we get to an example, it might not be till Tuesday before we get to this particular need, but we need a text file that we can read stuff from. For an employee example, so I'm going to jump ahead a little and throw together some names and pay rates. That's what we're going to read off a text file, and an example that we probably won't get until Tuesday. But we can go ahead and make it. So maybe there's like a Sally who makes $22.34 an hour, and a Bob. I'm just making names up. These do not relate to any particular people explicitly. I'm actually thinking of actors and actresses when I do this, people I've never met, but using that to pull up some common names. Maybe there's a Bob who makes $17.34 an hour, and David that makes the same as him, and Becky that makes $23.45. That'll work. So I'll say this is a text file and say this is our data, which is something that it didn't show up in the earlier classes, right? If we needed some data to work with, we put it right into our program, kept it in our program, and basically kept it in RAM. But RAM's not for storage, RAM's for working in. So whenever we have a bunch of data, it's much better to keep it over in storage, which is our next topic, the data structures. The idea of them is to get our data from storage into RAM, processed, and back out of RAM as efficiently and quickly as possible. So putting some data to work with over in storage where it should be. And then this will also work nice for the example of actually fixing a problem when with those exception handling blocks. What's this going to be? I'll call it employees.txt. Again, this particular data relates to an example we probably won't get to into a blue stage, but it fits nicely with this idea. So maybe our software entirely depends on it. The example we're going to do on Tuesday is going to entirely depend on that file, which technically does fit the definition of database. It's over in that hierarchical directory structure, which is an organized format to store data. So data can be stored and retrieved from there. It fits all the definitions of the word database, but hierarchical database in particular, but we would never call it that. But our data is over in a database, so maybe our file depends on it. So we need to read that file. So that's the first thing we'll do. yeah, I'm gonna do it this way instead of just reading it directly. Actually, I'm gonna do it the other way so I don't have to type all of that. So I'm gonna grab that, the file dialog, just use the ask open. It's a whole lot easier that way. It feels more accurate than manually typing in the name of the file and stuff. So ask open file name. If you haven't used that much before, this is an error I've made many, many times over the years and just made a couple weeks ago. So I know I still haven't committed to memory. When we open a file dialog, if we're going to use our regular Python open for read mode or write mode, make sure you ask for a file name, not for file. If these are different things, and if you try to use that file, do the actual file one and try to use that like a string, it'll throw an error. So we want to get the name of that. I don't think we need any parentheses, but we should probably keep that somewhere. So file name, actually, file path is going to be that open a file thing. And then we'll just read it. Open whatever was selected for read mode. It's from file. Give our handler some sort of useful name. And we know what's in that file. It's a bunch of names and rates of pay. If you didn't recognize that when I was typing it, that's what our coming example is going to be. But we probably won't get to that for later, but I guess for this case, we can just say maybe print a little hello world thing. Open that as from file. For line in from file. This all stuff we've seen before. We'll just print out a message. Name is line split on a comma, and we want the first thing in that line. All that should look familiar. Let's go ahead and grab that and print out a message. Print my hello there plus whatever's in that name. And just for an extra layer of precaution, since we're talking about error handling, even though I know it's a string, I'm going to go ahead and cast it to a string anyway, just in case the interpreter decides, oh, this is a number. We should do some math with this without us explicitly telling it to. Oops, what is it? I'll just call this exception. Can't think of a good name quickly. But when we run this, oh, that went behind there, didn't it? I forgot it did that. You know, our little open dialog, but that opened up behind there, so maybe I should just type the file name directly in there. We can go open that file. Then come back to the IDE and see it read through there fine. I guess I shouldn't do that. File path is, I was in the same folder I was using. Employees.txt. That way that box isn't opening behind the window, because that does seem a little strange there. So when we run that, that works great. No problems with that whatsoever, right? But we're usually not making software for ourselves, right? We don't pay ourselves to make software, for one. So we're probably making software for other people, and we don't know for sure what the user's going to do, right? they might be going, be going through their folders on their computer sometime, and maybe they're running low in space and looking at stuff, and they're like, oh, wait, what's this file? I have no idea what that is. I don't need that on here, and just hit the delete button right there. And we can't really trust our users not to do that. But then when we do that, that causes a big problem for our software. We can't, this software can't run at all if that file's not available to read. Let me recover that file now. So that's where we would put exception handling in it. So instead of just saying open that file, we're going to say try to open that file, except one of our exceptions. We can put them in specifically. So like, well, file not found there. When we throw, that's one of the best ways to do it. If you're going to be explicit about it, you throw every error you can think of and see which ones it is. So file not found error. So if we throw that, do I need a space in there? I don't think so. Alternatively, what I usually do is just do one catch-all. If we just say except, that will catch any exception that happens. But we can explicitly say which one we're looking for, and then do different things. So when fixing stuff, it might be important to do different things. But if we can't find the file, our software entirely depends on that file. Should probably make sure we can find it. So I'm going to switch this over to a function. Define, I don't know, say hi, give it a name. I'll move all this stuff up here. And that's what we're going to try to do, is call that function. So we want our software to do. And well, we can see that y'all have seen this before. When with no exception handling, all it did was stop running the dope message, which is what textbooks and tutorials always want to do here. They want to say print the file was not found, which can actually go even further. So if it's there, it works fine. But again, if it gets deleted, which we can't really trust users to do, then we get that the file was not found message. Which now that when you're first starting into Python, those tracebacks look like a mess. But when the message just says your file was not found, that's even less useful than the original message that it spit out. But it did the same thing. The software stopped running and spit out a message. So what we really want to do with that, when we're not under tight time constraints, like a tutorial typically is, or under tight page restrictions, like a textbook is, we want to try and fix our problem. So what I'm going to do for a case like this is I'm just going to fix that problem. I'll make a thing called data. Come over here and I will just make that string explicit. So it starts right there. Then we have a line feed. Another line feed. Another line feed. And then that. So that's what's in our file. A very short case this time. when I did this in the PHP class, I wasn't thinking ahead, and there was an entire, it was a third of an HTML file, a rather large HTML page that we needed created. So it was a big, long mess to put that in there. Probably should have done a short example like this. So sometimes it gets to be a mess, right? And now, maybe I'll print a message a bit. Print a message work like it was supposed to. So we can see when that file's there, it works like it's supposed to. When it doesn't work, I know what data is supposed to be there, at least the default version of it. So if it doesn't work, I'm going to rewrite that entire file. With open file path for writing this time. There's 2 files, set up our handler, and then 2 file dot write, all that data. Does that make sense? So sometimes that could be really, really long. When I did this in the PHP class, it was about a third of an HTML page that needed recreated. So there was a huge long structure there. It's like, well, why not just use that to begin with? And the thing about that is, hopefully this code never gets called to begin with. Just to be on the safe side, we probably don't want to put this whole thing into that function. So I'm going to move that back like it originally was. And the function will just do this with the data we pass in. So if we have the name, pass in the data we want. So kind of restructuring this. So what's hopefully going to happen is we read from that file, grab a name, pass into that function, and get our message. I know a rather trivial example, but hopefully you can see how that scales up. Because in this case, this exception handling can essentially do the same thing. Because after we write that file, we could split it up. Call it stuff is data.split new lines and comments. Do I need square brackets to do that? I think I need that. I'm used to doing it as just one symbol when I explicitly do it, but I think I kind of have to treat it like a regular expression. So I'm going to split that data on commas and new lines, which is basically where it's split anyway. And then I'll just walk through there. So say hi with S. Oh, that's not going to work. Guess I don't even have to worry about that. Get the lines, and then stuff is lines dot split on a comma. Yeah. And then we needed a big 2D array to walk through, so for L and lines. I don't even need this, do it. It's this. So basically, you can see we're doing the same thing, right? Name is lines.split on a comma, and we want the first thing in there, and then say hi name. I think I got everything there, back and forth a little bit. So sort of an ongoing process, thinking it through. But notice how the entire same thing happens. Okay? What's hopefully going to happen is we read that file and then print out the message based off everything in that file. But if that doesn't happen, well, the first thing I'm going to do, I'll move this up here to indicate it. First thing I'm going to do is try to replace that file. But since I have the data handy, I'm going to go ahead and work with it this time. So if we have to replace that file, it's there for the next run. So we have that extra message here that says it worked. We run, works like it's supposed to. But then there's that situation. People like to go out and take a bunch of pictures, go hang out with friends, take 100 pictures, get back, and they don't put it on the hard drive. It's like, oh, I need space. The user's going to start going through there, and it's like, oh, I have no idea where this file is. It can go. And then the next time they come to run our software, wait, why did I get an error message? I think I missed my syntax there. I almost never do that. What? Oh, sorry. Did y'all see that? I tried to read the file instead of write it in the exception handler. So it was still the same error happening. Let's try that again without the typo in. Yep. Okay. Reset that. So the file is there. Sorry about that. It would have gone a lot smoother had I not made a bunch of typos along the way there. So the file's there, so when it runs, it does exactly like it's supposed to. But if that file gets deleted, try this again, and for some reason it's not there, or it got moved, or some folder along the way got renamed. When we run it, the software still works exactly like it's supposed to. That's what we want to do with exception handling. Tutorials and textbooks for the need of concise and time restrictions or page restrictions. They have to be short and abbreviated to go with that basic syntax, but that's the sort of thing we really want to do with exception handling. Because to the end user, well, to us right here, I had to put an extra print statement in there so that we could see it worked like it was supposed to. And the problem is fixed. So we run it again, now it's back to work like it was supposed to. But to the end user, if that special echo wasn't in there to let us know whether we did the try part or the except part, they wouldn't know the difference. So it takes a little bit more. You'll notice it's pretty obvious that our exception handling is longer than our actual software. That might happen sometimes because, and the, I guess if that seems aggravating, that the exception handling is more than the actual software itself, maybe also add on top of that, icing to the cake there, that hopefully that code never runs. Because that's what we're actually hoping for. That this code will never, ever run. We hope that this code runs every single time and this never happens. But when it does, we don't want to just spit out a message. We never want the end user to see a message that says the program messed up. We want something that fixes it. So sometimes exception handling might get really, really big because that's what we want to do. We want to try to fix the software, fix the problem so that no matter what, the end user cannot tell it hit a problem. Hopefully that makes sense and kind of, you can see how that can build there, and that can be a long winding process. It doesn't really fit good in a classroom to do that every time because, like, you know, if we're a project that takes 6 months, we might get the original part done in 2 months. Then some debugging, refactoring, and then coming back and doing this, fixing every possible problem that we can figure out, that we can think of that software encountering. That's the bulk of the time for modern software, because we want it to run. We don't ever want our end user to see our software crash. Because hopefully it'll be like this: work like it was supposed to, 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 work like it was supposed to. So that larger section of code where we fix the problem will hopefully never ever run. But hopefully it's very evident and obvious why we want to have that there. So you don't want to just print out a message, actually fix the problem when you can. What did I do wrong on my statement there? Is it file not found error? I guess I have to delete the file to get that. Okay. I did parentheses first time, didn't I? Started working in C# again. First 8 weeks, I was pretty much doing Python all the time. Oh wait, no, we were doing HTML the first 8 weeks. Jumping back and forth between languages, they start to blend together. I wrapped that in parentheses like I was typing C#. Because over there it's still called a file not, well, no, it's a file not found exception there. But I've been waiting to show that because that's one that always seems a little off to me with what tutorials do. And it makes perfect sense as to why. I mean, a tutorial has to be short and to the point. So they can't make, they just need the basic syntax and leave that for the programmer to fill in that gap. That a print statement usually isn't enough. Hopefully that was enough that y'all can see the value of it and the necessity of spending that much time on it. Okay, so moving on to our next set of content here. I'm not saved. Oh. Oops. The introduction page on the notes. There's no introduction page on the notes. It just jumps right into the content. So I know what the introduction is. So getting into our next big topic here. Data structures. The short definition on this, the one you're probably going to think of unless you have to actually recall the technical definition for a test or something. One we think about is data structures. We can just do with a comparison. Data structures are to RAM as databases storage. That's the quick one for keeping it in your mind when you're working on it. The things for keeping your data around long term. This is the short term version. Volatile storage or short term. And opposing volatile storage, we have stable storage or long term. Actually, we usually call that non-volatile, but I just decided to write stable as I was writing that out, just split it up even further. So that means the same thing, right? Volatile and stability, opposite versions. So here is where we keep stuff around. That's what we're looking at the past couple of weeks. Putting things over in storage in nice formats. JSON is eventually popular. Most software development, most things right these days are probably going to go with JSON. JSON for the storage and Python for the scripting. That's definitely the most popular format, but things are always changing. There's different new alternatives being invented as we speak. Oh, speaking of which, I'm going to show something. A side step before we jump in here. I was going to show this right at the beginning of class, and then I suddenly forgot. Right before class, I was just kind of looking at staying up to date on the field. It's important in any field, and y'all have an assignment on it. So I thought I'd point this out. It's only been about a week and a half ago was NVIDIA's big conference, their big yearly conference where NVIDIA announced everything they've done in the last year, what they plan to do for the next 5 year, announced their next 5-year plan, what's coming up and stuff. So the review of their big conference came out today, and you all have that new technology report due. So that is definitely some new technology that might be good for that report. It was on sdtimes.com. It's the second article back on the list, at least right now. I was going to show that at the beginning of class, but that's new technology. The stuff, NVIDIA announced their 5-year plan and all the latest stuff they've done a week and a half ago, 2 weeks ago. It was the last week of March, but the review of it came out today. And you all have that new technology report, so that might be a good one to summarize in a paragraph about new technology. It's looking ahead, some interesting things there. Sorry, got a little distracted. I meant to show that earlier and then something reminded me about it. But we looked at the databases, storage. Storing our data. Oh yeah, that's what it was. Most popular anymore, JSON and Python. So y'all, I think we're already familiar with that. But once we have our data stored in a JSON file, which we would often refer to as a NoSQL database. It's a non-relational, unstructured database. So typically we say NoSQL for no structured query language on that one. But when it's over from there, we need to get it from there, from storage over into RAM, do what we're going to do with it, and then get it out of RAM so that our resources are available to do other things. So that we're not just hanging out in memory, wasting space. So that's gonna be the more technical definition. The method, I'll say tool. Tool to get data into, around, and back out of the CPU and RAM and all those working pieces, CPU, RAM, the control unit, the arithmetic logic unit, a whole lot of things that we want to use those resources and then get our stuff out of the way so that those resources are open for other things to use. Back out of that as smoothly as possible. And if you go look up the technical definition, it's similar to that, but you'll see the word efficient there. And more in our world, we don't care about efficiency as much anymore, right? I recently had a computer break and had to run over to Walmart and grab the cheapest computer they had at 6 o'clock in the morning. So it was before any electronics people showed up or anything. I guess it's on device manager. Had to get a manager done like the thing because I needed it first thing in the morning in a rush. So I just bought the cheapest computer off the shelf at Walmart. And there are no details here. Oh, I was hoping, I figured there'd be some stuff here on this list. Oh, that's not the one I wanted. Arches menu system. There we go. This has it. I was trying to pull up a different list, but it's not, apparently not in the spot I thought it was. But the cheapest laptop they had at Walmart. 3 gigahertz with 8 gig of RAM is the cheapest one at the store that sells generic stuff. Right? Efficiency is not a concern like it used to be. So test questions and things, keep in mind those are probably still going to say efficiently, but we really don't care about efficiency like we used to. So you might need to look for other words, but as smoothly as possible. We want to keep our code nice and clean, get things in there, out of there. We don't want to be wasteful though. We don't have to worry about efficiency the same way we did in, say, 1989, when RAM was a precious commodity and transfer speeds were a phone line at best, 56 kilobits per second at best. We don't have to worry about it like we used to, but we don't want to be wasteful either, because there are still plenty of problems we could come up with that would grind this computer to a halt, even though those numbers are much nicer than they used to be. We have a long list of things. You've probably heard some of them before. Stacks and queues. Stacks are going to be one of our main ones, which the fact that you've already heard of that and know what it is probably makes it seem strange to cover the class. It's like that textbook needs to be concise thing that we just went over exception handling for. The textbook, our textbook does show a custom stack object, but there's nothing really special about it. The reason we study that, aside to just learn a little, look at it in a little more depth, one of our common tools, is when we so we can customize our classes. The stack that's or things that will behave similar to a stack built into the language, in our case Python, they're generalized. They have to work for every purpose. And whenever we use them, we're not going to need them for every single purpose at once, which means there's things in there that we're not going to need. So there's a bunch of overhead coming along there that we could strip down and minimize and use our own thing with. So that's where we'll start at, is just the core concepts of a list. In particular, we'll look at a linked list. They'll probably use this one for stacks. I might back off and just use the list built into Python for the stack and view and other ones, but probably easier if we use the built-in ones, but that'll probably be next Tuesday. But we might build it off this one. This one will already be built by that point, so it won't matter whether we import and use this module, the module we're going to build tonight, or the one built into the Python language, right? They already, both of them, by next Tuesday, both of them will already exist and be there, so we can just import and ask for them in our code. Very similar to what we would have in Python by default. But it's kind of customary to create these in programming classes, study some of the concepts, see how they go together. And then the usefulness I already mentioned, we can customize a list to better fit a particular situation. So then we don't need to combine, then we don't need that overhead. If we combine our custom object, which is a data type, right? That's the data type we're going to use in our program. That sounds, when talking about an object or a class that way, a class definition, that sounds an awful lot like it fits this definition, right? It's a tool to get data into, around, and back out of our processing components as smoothly as possible. So yeah, we've already seen that data structure. It's so popular, we don't even think about it. We separate it from our other ones. But we can customize that, and we don't need an individual one. So like the example I had in mind was, we keep doing business related things. That seems like an easy thing to do for Americans to relate to. Right? We all have to work. We want to eat, and we put gas in our cars and all that. So most people are familiar with the whole job concept. And one of the things, we made an employee object, right? All kinds of child wounds, and we could customize it really nicely. But employees don't come as an individual. A sole proprietorship, a business, entrepreneurs might come as individuals, but that whole time that entrepreneur is going to be hoping that their business grows and they can hire employees, a plural. So we really don't need a class for a singular employee. What we need is a class for an entire crew. So instead of that singular employee thing, we can kind of extend that so that we have the capabilities we need of a list built into our data type. Then we don't have to use that built-in list, which has a bunch of preset things. I shared a video with you all about it. I don't know if you all watched it or not, but there are certain sizes, right? Did you all see that video by M-Code? There are certain sizes where we can take elements out of our list and it actually gets bigger. Or a certain size in memory is going to be needed. Like if we need to store 3 things, Python's going to automatically give us space to store 8 things. If we need to store exactly 8 things, Python's can automatically give us space to store 16. So there's that little overhead. But if we know more precisely our situation, we can bypass that overhead and improve this smoothly part, which again, technical questions, think efficiency there, but that's getting out of date in our modern world. I just showed you the numbers from the cheapest laptop at Walmart. Efficiency is not a big concern. So a linked list, our definition here is an iterable collection of elements where each element contains a pointer to the next element. And a null pointer marks the end of the list. Okay, quite a mouthful. I wanted to make sure I can get that one precisely. Is definitely expect this definition on certification exams. And that's cross language. You take language certification exams. The formal definition of a linked list is one of the things you probably expect. So I want to make sure and get that whole thing up there correctly. An iterable collection of elements where each element contains a pointer to the next element and a null pointer marks the end of the list. Probably used to hearing null pointer from one of our errors that happens. It doesn't have to be an error. Just, well, if I draw the big stack heap diagram for a linked list, that's probably only going to get up to the linked list tonight. So go ahead and move over here. That way I don't have to erase the board. If I go ahead and draw the stack heap diagram, which I know a couple of y'all have had me since the SDEV 120 class, several programming classes, and know that I've used this right at the beginning, but stacks and heaps, those are types of data structures. Oh, well, that's not on the video. I was pointing out that label again. So y'all have been seeing this for a while, but we're just now getting around to talking about what data structures are and getting into some more of those details. Just a reminder, the stack is where we stack up our instructions to run. We're going to talk about stacks in detail. It's the second thing on this list of yellow notes. And a heap is dynamically allocated. So a heap changes, they're a little more complicated. We're in a 16-week class, so I think we might have time to look at heaps, at least super basic versions. But it's not one of the ones on our actual list, so that one's going to depend on time. But again, it's it'll make sense after we look at the other data structures. Once we get there, if we run short on time, I could just rattle off a few key points about it, and having seen linked lists and stacks and queues and a couple things about trees, you should be able to figure out how to put a heap together automatically. So in our code, we'll have in our code, we ask for some sort of list which has a pointer. So yeah. So they're actually different types of pointers. So this one is a reference pointer. So I'm going to draw the arrow, a big arrowhead like that to signify it's different than this pointer. But that's going to point over at this first element. I'm going to call it node 1. This element is going to be really long to write. When we write our code, we're going to call each one of these elements nodes. That's just sort of a standard thing to call them. And then that way we're using the same word consistently across all our data structures. Node makes a lot more sense in a tree or a graph. But it doesn't not make sense here. So go ahead and call in our linked list elements nodes. Makes this section more consistent. So that's fairly standard. The node is going to contain 2 things. Which I'll go ahead and write out the class. It's not much. We're going to make it in a moment. We're going to make a simple one and then a bigger one. So our class node, we set up our constructor, self, and then it'll take in some sort of element. And it's not as obvious here in Python as it is in some of our strictly typed languages. But then we have 2 things. So obviously self.element equals this element we passed in. We also have self.next, which by default is going to be none. By default needs to be a null pointer. So that's all the code to make a linked list. To start with, obviously we're going to want some custom methods there, but a null pointer that points to the end of the list. So when we make our first one, we have that, and then we'll set it up to point to the next one. So that's what's in there. The null pointer or the element, and then a pointer to the next one. Not that big enough to get some words in. And it'll point at node 2 up here. I should probably try to make that kind of precise. It points at the next element, which then points at node 3. And that's probably enough. Then that one just points off at empty space. So we have a start to the list, a clear definition of each one, a well-defined start, and an end. So it's an iterable collection. And you'll notice here, with Python, we might have to think about the data type a little. If we were in a strictly typed language where we had to say what type of data we have, hopefully you'll quickly realize that the data type of this one is node. So that's another reason this one's commonly studied, because the data type we're making uses itself in its own definition. A self-referencing data type. Then we can do some things with this. This is a singly linked list. Singly with an Y, singly linked list. We also have doubly linked list, which probably realize very quickly neither one of those is an actual word in English, but that's what we call them. A singly linked list points at the next thing. A doubly linked list has next and previous. So a doubly linked list would have
a previous pointer that came back to 0.1. And that way it shows going in both directions, which behaves a lot like the singly linked one. When I do the next little example here, it'll hopefully make sense. Did I have any colored things? In my notes, I used 2 more colors to do these next steps. See if this works. Okay, yeah, looks like red works. So we can start at the beginning and walk through our list because there's a well-defined start and well-defined end, and each thing points at the next one. So if we wanted another element, and not just wanted another element, we wanted it at a certain point. We can just go in here and change what this points to. So instead of pointing at node 3, node 2 comes up and points at node 4. And then node 4 comes down, the next on node 4 comes down and points at node 3. Which we're going to see that directly in the code here in about 5 minutes. That's all it takes to add another thing into that list. And obviously it's even easier if we add it to the end, because we could just put node 3's next element is node 4. That one is hopefully fairly trivial. So I'll leave that off the picture. Adding to the end should be obvious. What about deleting something? What if we wanted to get rid of node 2 here? Like, okay, actually we don't want that in there. All we have to do is get rid of that pointer to it. We cut our pointer there. Is this all still in there? Did I get too low? I can't quite see what's going on in the video. Oh yeah, it's still on there. So instead of node 1 pointing at node 2, we have node 1 point at node 4. Because we iterate through this list by the next one. So we start here. Next now goes to node 4. And the next from there goes to node 3. And the next from there is a null pointer. So we're finished with the list. So we've been using lists for a while. And just using them, we typically don't slow down and pause and think about what's going on the inside, but that's what's happening on the inside. There's just some pointers. If we need to add something to our list, we point at something else. If we need to take something out of our list, we just stop pointing at it. So, not a super complicated thing, right? So let's make this. I'm going to do something real quick though. I might refer to this picture. So I'm thinking what the easiest thing to do instead of stopping the screen share. That'll work. I'll just take a screenshot of it here on my computer. Save that. See. There we go. That seems like an easy way to refer back to that instead of stopping the screen share. I'm not sure if I'm going to point at it or not, but y'all have seen what that picture is. I know what's going on there. But let's see this in practice. Yeah, in the paper, I wrote that down like I was gonna write the Python code on the board, but that's the very next thing we're getting ready to look at. So I guess it's kind of trivial to write it on the board, then turn around and write the same Python code on paper, but this is the code to create a list. We create each element, a spot for each element in the list, and then a pointer to the next thing. And then a doubly linked list, it points at the stuff before and after. Then we could do things like iterate through and create a counter, is how we get the indexing and things like that. But we'll start with just sort of a basic stripped down version because. Oh, well, that's screen share. Did I close Spider? Oh, there it is. Let's see. So done with that for now. Done with that. We'll come back to that file and give this a name. Folder. April 7th. Oh, wait. I call it data structures. That way it can be found on the GitHub link. If you go in there. And I'll call this first file the same thing. We'll just make a module of our data structures and import that somewhere to use. So, like on the board to create a list, in particular a linked list, we can just create a class, we'll call it node, and there might be better words for a list, but as we study more data structures, node will make more and more sense in other places. So it's customary to just use node here as well. That way we have that same name for all of our structures. So a linked list. I guess I should probably call that like LL node or something. I'll modify it a little. We're going to create an LL node. Then we just need a constructor. We've seen constructors, and this one is already written on the board. So all we need is the element that is going to take this particular spot in the list. So self.element, and self.next. By default is none. Then when we add more stuff to it, we'll add some stuff. Just to have a little bit extra, I'm going to go ahead and make a print method. Or go ahead and make our toString method. And this node holds plus whatever's in that. And make sure and cast it because it's a list. It should be ready. A list should be capable of holding any of our Python objects. So we make sure in simple cases, we probably might have strings there, but we're probably going to have more complex objects in our list. And that's it. Now we can go apply this. So I'll make a new folder, or not new folder, a new file. I'll save this so I don't forget. I'll call it testing. Test linked list. Might as well give things descriptive names. So obviously we need that module we just created. Data structures as DS, because I don't want to go type in data structures every time. I feel quite certain that I would make a typo if I type that whole word every single time. So we can abbreviate it and make it a little easier to code. And then if we want our code to be highly readable, write all our code with DS, so we're less likely to make a typo. Then hit Control H and replace all those with the whole word later.
and take that as part off. That way the code's more descriptive as we read through it. But the computer does all that extra typing, so it wouldn't make a typo. Then we can just make some of these things. I want number 5 is es.node.ll node. With, I'll just put some integers in there. I would say a simple example of a list. We're looking at, I guess one of the big things here is how simple it is to make a list. It does not take much at all. 5, 3 is ds.ll node with a 3 in it. 17. That would give us a good start. ds.ll node of 17. And then we need to actually load it into our list. The first thing is where we start at. The traditional term for that is the head of the list, the starting point of the list. Head and tail are the normal names. So on our picture, oops. The front of the list is the head, and we kind of go all the way through our list. And the end of the list is the tail. Some standard terminology for that. So we'll start with 5, and then we can have 5 point at 3, and 3 point at 17, and 17 can just point off into nothing. So we'll print that out. So our current node is obviously it's a list. We want to iterate through it. That's one of our core things with the collection. Our current is going to start at the head. Actually, we could probably leave this line off. Yeah, I'll just do it this way. Oops. Current starts at the head. And then while current is not a null pointer, which in most of our languages would actually say null or null pointer, but in Python it's the word none. So while current is not none, which remember is our default version if we don't assign it to anything else, I'll just print it out. Oops, not in that line though. Print whatever is current, and then move current to the next thing. Equals, all right, dot next. There we go. The ID was determined to put a parentheses there. I was not typing parentheses there. Next is just variable, and in Python we have that nice direct access to them. Let me clear all this. There we go. So kind of what we're expecting, just a bunch of elements in a list. You can see it up here. The elements are separate though. I guess one of the big points of studying this is to show there's not much to a list. It's not a super complicated thing to create. Okay? We didn't actually need these lines. That first part created it, and then anything else is just extra stuff. So something that could internally loop through, and count how many elements are there, and then give each one a number. Give your first one the number 0, and your last one less than the length of however many things you have, or just keep incrementing the counter. Right? On the way through the while loop, increment a counter, and then add a data field so that the value from a counter on a while loop corresponds to each element in the list, and then you have an index list like you used to live with using in Python. And then you can just keep adding the functions that you need. You can see there's not much to actually creating those. What was I going to do here? guess we can do that stuff on the board. I'll print out some spaces, print, add a note. And just like we saw on the board, when we want to add a node, that's what happened here. So instead of pointing at node 3, we got rid of this pointer and we pointed at node 4, and node 4 pointed at node 3. So we just pointed at something else, added it in on both sides. Hopefully you see that sticking it at the end would be a step easier than what we're getting ready to do. So we'll just look at one in the middle, and then the end is a trivial situation because we don't have to do anything else afterwards. So I'll make something called 12. There's a ds.ll node, a linked list node with just an integer. That'll probably work for now. And then we can say, so this was our second node. I'll kind of match that picture. So node 2 now points at the fourth node we created. So we'll just switch that around. So 3.next switches over to point at 12. And then 12 points at 17. And then we'll just look through the list again. Yeah, I'm gonna, instead of head, I'm gonna go back to point at 5. Because that line's not really doing anything. Except showing us the common terminology. So think of this picture over here to remember the terminology, because you might see it on a certification exam or something. This picture of all those pointers, think of it like a snake. Front of it's the head of the snake, and the back of it's the tail of the snake. And it just kind of winds around through our gram and stores all our data. So head and tail are the proper terminology there, but we can change it any way we want to. So I'll do this. So here's our original list. We added a node to it, and you see we're still just iterating through a list. So internally, obviously, when we have a pre-built one and all those functions are ready for us, that's going to be shorter. But you can see internally, there's not much to this at all. We can delete something. Print a couple line breaks, and print different start. So to get rid of 5 from that list, I could just point at the second thing. What is our second thing? 3. So we just stop pointing at something if we don't want to use it. Instead of starting at the head, we'll start it. Or instead of starting at the first one, we'll start at the second one. Or oops. Add some white space down there. Print. Oops. A little bit of space between them, then delete it. Delete a node. And to do that, we just point at something different. So if we wanted to delete 3, we could make 5 point at 12. And then sit through the list again. So you can see there's not much to that, making a list, but one of the big reasons we study is the ones built in the language are very generalized. And if we have big messy situations where we need to start worrying about stuff, big complicated things, we might want to work with something very specific. So we can make something very, very specific. A customized list or like a customized data structure. So that one I mentioned earlier. I'll do that here. Custom linked list built into object. We're probably going to make some custom classes anyway, right? Like an employee. The thing is, for businesses, employees are very regular. It's very rare that we would only have one employee. We're going to have lots of them. We're going to have lots of employees adding up into a crew of employees. So we can put those features together for a linked list right in there. So find a constructor, self, and then our employee, I guess a name, a position, and a rate. And self.name is name. Self.position is position. Self.rate is rate. So up to this point, it looks like what we would have for a single employee object, but that's also what was included in just one line up here. So it's really this next line right here is what makes it a list. We have our data type. Like, okay, that's what represents an employee in our company, but we have a bunch of them. So if we make a pointer, something to point to the next one, now our data type is the list in and of itself. So we don't need to use an external list to work with it as a collection of things. So ultimately, it's even shorter than what I pointed out earlier. To turn a data type into an object takes one more line. To turn a data type or an object into a list takes one more line of code. Then whatever custom features you would want for list type things to work with it. Oops. For us here, I'm just going to do a string so we can wrap this up in about 5 minutes or so, maybe less than 5 minutes. So what's a good way to represent our employees? Obviously, self.name. We'll start there. Is the plus self.position plus and makes plus self.rate plus per hour. Or you can use printf. The reason I didn't use an F string is because I tried to use an F string in the SDEV 120 class. That one was too fresh on my mind and tried to use it in the SDEV 120 class without showing it with people, showing people what it was. So I had to quickly delete it and then go back to the normal one. So I was like, I should force myself to switch back and forth between them more often and pay closer attention. I've also noticed I didn't jump around. So I noticed an issue, right? Programs are about problem solving. So anytime we're solving problems, it's going to improve our programming abilities. When we encounter little problems, even with the way we write code, which in my case was writing code for examples in classes, I tried to do something that the people just getting started in Python had not seen. So I thought I'd focus on doing that, and it's adding that focus back in has done something I haven't done in a long time, which is the casting before typing the data type in there. You'll probably see me do that a lot. I type the data type and then come back and cast it afterwards. That's just the way I've wrote my code for years. But, you all know about the format strings, so you just put F in front of the quote marks and those curly braces, and it makes everything look much nicer. While I'm thinking about it, I forgot to do it in class, in our other class, Mark. In C#, put a $sign in front and the curly braces in your string, and you get the same thing as you do in Python when you put an F in front. It'll make your C# code a lot nicer. I forgot to say it in our other class, but y'all know about the format string. Sorry, that was a complete sidetrack that randomly popped in my head that I realized somebody in the roster right now would find easier. So yeah, a $sign string with curly braces is the same thing as F string with curly braces in Python. Our languages are very similar. We can dive back to the Python class that way. We have the same functionality in the different languages, just slightly different syntax. In Python, we put an F out front. In C#, we put a $sign out front. So that gives us our custom object, which we included that one line of code to turn it into a list itself without using Python's built-in list. So I'll come over here and do something with it. I'm gonna look at my prep work, so I'm gonna pull that up so I don't make a typo and end up taking a long time. But basically the same thing we did above. Print, custom class int list combination. Stick a label on here so that it's clear what we're doing. And then we'll just kind of create those. So one of our positions is going to be the boss. So that seems like a good place for the head of the list. ds.crew, name, Sally. Sally's the manager. And she makes pretty good money as the manager, 45.67. Seems like a good salary. Our administrative assistant, which the old term, which who thinks it is, yeah, I'll spell out I'll say secretary. That's easier to spell. A very important person in any company. A good thing to remember as you go into the business world is it doesn't matter who you are or what you do, you can and will be replaced easier than a good secretary. Good secretaries or good administrative assistants are really, really hard to find. And everybody else can be replaced much, much easier than a good administrative assistant. People often forget that. Let's see. I don't know. Is the administrative assistant? I'll spell it out. Spell it out here. And I don't know. Maybe she makes 22.34 now. I have no idea how much administrative assistants make. Probably more than that, because it's an important position. You don't want to lose a good administrative assistant, so you usually pay them well. Laborer 1, that could be Bob. Labor, and I don't know, 34. Oh. Hey Dylan, that surprised me when you came in. Usually we're about finished by this point. We're looking at custom data structures this evening, a whole bunch of content stuff, so you might want to check the recording. We're about a minute or two from finishing up here, as soon as the next bit of code runs. Labor 2 is ds.crew. Thank you for coming though. At least catch the end of it. So we created our own list instead of using the one in Python. So that's what we're going to be studying for the next couple of weeks is those data structures. We have some built into Python, but we'll look at what we're doing with them. Because it does not take much code at all to create that. And when we use them, especially as new programmers, it seems like a big complicated thing. So finish up here, give our other laborer name. And I'll give him the same pay. So that's enough. All we're gonna do is print this out, but I guess I could still at least pretend like our example isn't as trivial as it is. Now we can set up our list. So to iterate through it, the next item in the list after the boss would be that secretary. The next thing after the secretary is the laborer 1. And the next thing after laborer 1 is laborer 2. And then just like we saw earlier, if we need to add things to our list, we just pointed a new thing. And if we need to take things out of the list, we just stop pointing at it. So making a list from scratch isn't at all complicated. So current is, we'll start at the boss. And while current is not a null pointer, well, in this case, we'll just print it out. Print current, and then jump to the next thing in our list. Whoops. Current equals current.next. I'll just go. Okay. It closed when I hit save. That was strange. I'll clear all the stuff out of memory so we can take a look at our variable explorer again. Oh. Resetting the current. So the stuff down here at the bottom. So you can see we get all the functions of our custom list of our custom data type, our object, intermingled with a list itself. So that idea of a data structure, a tool to get data into, around, and back out of our processing component, that's the hardware, as smoothly as possible. So keep the word efficiently in mind, but efficiency doesn't matter like it used to. When I learned to program in the late 19, when I first learned to program, first started using computers, which back in 1987, basic computer usage counts as programming today. What was turning on and opening files back then falls into the category of programming today. But RAM was a very precious commodity, or we didn't want to waste it, so we had to. Efficiency was always a major concern, but well, earlier today we saw, I pulled up what the numbers on the cheapest computer they sell at Walmart is. And efficiency is not something we have to worry about. So I'm going to use the word smoothly in our definition. But that's what we're going to look at. The textbook, I think our textbook had this part, just that basic, what it takes to create a list. But the reason we study that, aside just from knowing what a list is after all the times we've used them, is that it's really just that line of code. We can add that line into any of our objects, and then our custom data type is set to be a collection. Is ready to be a collection.
and the first one we're studying here, which is a linked list structure. And I'm going to the definition of that one more time. An iterable collection of elements where each element contains a pointer to the next element and a null pointer marks the end of the list. I was very careful copying that definition. That's one to expect to see on a certification exam. Actually, all of the formal definitions for going over data structures, I'm going to be very careful with those, and I'll keep repeating it like I did on this one, because those are definitions you should expect to see on a certification exam at some point. But that's what a linked list is. It doesn't take much to create it. So instead of using the built-in ones, we can just extend our objects one more line and create our basic data types or objects, turn them into more of a traditional collection sort of thing. That's the first way. Next two we're going to look at are the two most commonly used ones. We'll get to that Tuesday. Stacks and queues. Maybe priority queues, but priority queues are just in order. Every time we add it's a queue, but every time we add something to it, it re-alphabetizes it or puts it back in ascending order. Every time we add something to it or take something out, it reorganizes it to make sure everything's in order, so that it's not necessarily first in and last first out. But that's obvious once you've seen a queue, and there's quite a few. We have a 16-week class, but we certainly won't see all of them. Stacks are next. We might look at heaps, but by the time we talk about quite a few of them, when I mention the terminology, you'll probably just immediately see how to put a heap together by that point. So that's coming up in the next few classes. We're just going to keep talking about data structures and looking at how we make them instead of using the built-in ones. And as you're messing around with stuff and doing things, keep in mind what we saw the other day on Tuesday, that we can take time measurements of what we're doing, and probably one more data structure or two more data structures. So maybe Tuesday, we'll also add in maybe CPU usage and RAM usage. Or at the very least, we could also get those numbers from Task Manager, or the equivalent. If we're in a Windows machine, we can get it from Task Manager. But we can get them right in our code. And just like the timing things, we want to start looking at which methods are better than others for certain situations. Because it goes back and forth, which is best. It is something that depends on the situation. So you want to look at some of those measurements and get familiar with it. Which ones are faster for numbers? Which ones are faster for strings? Which ones are faster for custom data types? Which ones use less or more RAM? Which ones that need more memory and which ones need more processor, CPU. So we'll start looking at those numbers. We finished the first half just looking at Python, accomplishing the task. But the next step kind of goes along with this as smoothly as possible. So not just accomplish a task, but can we accomplish that task as smoothly as possible? Are we doing it in the optimal way? Otherwise, does anybody have any questions about this evening? The stuff from this evening? Okay, I assume the silence means no questions. So y'all have a great weekend. And if you have any questions, let me know. Otherwise, I'll see you on Tuesday. Over.